All right, so next thing I want to talk about is how we go about assigning probabilities. So here's an outcome of what we're going to cover. So the first thing I want us to note is that a probability is a numerical measure of the likelihood a specific event will occur, right? It's always going to take on a number between 0 and 1. A probability of 0 means the event will not occur. It will never occur. There's no way I'm going to flip a coin and there's no way I'm going to roll a 6-sided die and get an 8, right? 1 means the event will definitely occur. You could even relate this to a percentage. 100% it's going to occur. And then the closer the number is to 1, so the closer your probability is to 1, the greater likelihood of it occurring. And we're going to use this notation, this PR, that stands for probability of event. Note, we don't just do P, because remember that stands for permutations, which we talked about last class. Nope, last chapter. Welcome to Teaching Online. So there's 3 different types of probabilities. So the one we're probably most familiar with is logical probability. So logical probability is obtained by mathematical reasoning, and it often uses counting methods. This is all the stuff we covered in Chapter 5. So if you are not feeling great about Chapter 5, go back and review it, okay? So one of those would be, say, for example, getting a full house in poker. So probably a coin toss shows heads. Those are examples of logical probabilities. Empirical probability is obtained by sampling or observations, right? It's calculated as a relative frequency. So a certain brand of light bulb will last 1,000 hours. So what we need to do is watch this brand of light bulb and see how often it lasted 1,000 hours. The probability it will rain tomorrow, maybe we would have to observe how many days it rained throughout the year, okay? The next one and last one that we aren't actually going to do much with because we can't really calculate it, right, is called judgment probability. This is also called subjective probability, meaning you're using your own information, your own kind of gut feeling to make an educated guess. So, for example, probability the Cubs will win the World Series. Probability you will get an A on your next exam, right? If you've gotten A's on all your previous exams, the probability is going to be pretty high that you get an A on the next exam, as long as you keep doing the homework. Do the homework. So when we find probabilities, we want to represent them with a probability distribution chart, okay? So let's suppose an experiment has a sample space S with a finite number of, that should be of, a finite number of outcomes, okay? To each outcome, we're going to assign a probability of that outcome, right? And we put these in a chart called a probability distribution. So here's the outcome. It could be our events. And then here's the probability of that specific outcome occurring. Note that if I add up all the probabilities, you're going to add up to 1. And that each of our P sub n has to be between 0 and 1 in order to be a probability. So let's toss an unbiased coin and observe the side that faces upward, okay? And I want to determine the probability distribution for this experiment. So since our coin is unbiased, each outcome is likely to occur. So my options are heads out of tails. You know, I have one outcome out of my possible sample space, which is a size of 2, right? Because I only have heads or tails. It's a little different for empirical probability. That would be when we conduct an experiment. So let's say I wanted to measure the volume of traffic on a major highway during rush hour. This could be really important information, right, to decide if we need to widen the highway, okay? So we're going to generate a probability distribution using data we observed over 300 weekdays. So the total of this is 300. So event 1, it looks like is there were greater than or equal to 1,000 cars, right? That's our first outcome. And the probability of that is 10.10. We took 30 over our total of 300, and we got 0.10. Outcome 2 is that there were 1,001 to 3,000 cars. That seems like a lot of cars. Oh, it keeps getting bigger. 3,001 to 5,000 cars. 5,001 to 7,000 and greater than 7,000 cars. And we found each of these by taking the frequency observed out of the total number of observations. So we have 45 out of 30, 135 out of 30, 75 out of 30, and 15 out of 30. If we convert all of those to a decimal and we took the sum of all of these, they're going to add up to 1. Let's talk about the addition principle. So if I have E that's an event and it contains multiple parts of our sample space, then the probability that that event occurs is the probability of all of the parts of that event, the probability of each specific outcome in that event. So let's suppose that we toss a red die and a green die, and we observe the number of, not the sides, yeah, we reserve the numbers on the sides that face upwards. I want to calculate the probability that two dice show the same number. So as I've done in a previous example, here's our sample space, right? Our sample space is 36. So each of these individual outcomes has a probability of occurring that's 1 out of 36. There's 1 out of 36 possible options that I could roll a 1 over 1. The event that any two dice show the same number is right here, right? There are only 6 ways I could roll doubles. And each of these has a likelihood of 1/36. So if I add these all together, I get 6 out of 36, which is 1/6. So the probability of me rolling doubles is 1/6. Let's talk about the inclusion-exclusion principle. So let's let E and F be any events. Then the probability that E union F, then the probability of E union F is the probability of E occurring plus the probability of F occurring minus their intersection, right? That means these events would not be mutually exclusive. We have to subtract the intersection, otherwise it's double counted. If two events are mutually exclusive, then I can just add their probabilities, no problem. There's no overlap. So, for example, let's say a factory needs 2 raw materials. The probability of not having an adequate supply of material A, I'm going to draw a Venn diagram, you watch. Okay, so the probability of not having an adequate supply of material A is 0.05. I don't want to fill that in yet. And the probability of not having an adequate supply of material B is 0.03. A study determines that the shortage of both materials is 0.01. What proportion of the time will the factory not be able to operate from lack of materials? So the probability of A union B, nope. Yes, the probability of A union B having a lack of both materials is going to be the probability of A plus the probability of B minus the probability of A intersect B. That's this right here, 0.01. So I'm going to take the probability of A union B. I have the probability of A, which is 0.05, plus the probability of B, which is 0.03, minus the probability of the intersection, which it gives us 0.07. I could also have found that by adding together all of this, right? 0.4 plus 0.01 plus 0.02 is still 0.07. So 0.07% of the time, so 7% of the time, because we multiply by 100 to get percentage, 7% of the time the factory will not be able to operate for lack of materials. That's really bad, right? That means it's only functional 93% of the time. Is that a good business model? No, but this was just an example. This isn't a real world problem. Well, it could be, but I think it'd be much smaller.